Welcome! In this video we examine airside improvements that reduce coil and reheat energy while safeguarding comfort and indoor air quality, the Economizer, energy recovery ventilators, and dedicated outdoor air systems. By the end of this video, you'll have the tools to make smarter, more energy efficient decisions when designing or operating HVAC systems. We'll start by tackling the challenge of per load operation, showing how simple reset strategies can slash energy consumption without sacrificing comfort. Next, we'll open the window to a powerful energy saving technique, Economizers. You'll learn how to analyze when and how to bring in cool outdoor air to get free cooling. We'll also look at the heat and energy recovery ventilators to see how we can capture energy from exhaust air to reduce the ventilation load. Then we'll dive into dedicated outdoor air systems, DOAS, a cutting-edge approach that separates the job of conditioning ventilation air from cooling the space. You'll see how this leads to major efficiency gains, especially in dealing with humidity. Finally, we put it all together using a new framework. You'll learn how to select the best airside strategies, whether it's TAV, VAV, or DOAS, that aligns with the building's specific loads and indoor air quality needs. It's about choosing the right tool for the job. By the end of this video, you'll have the tools to make smarter, more energy efficient decisions when designing or operating an HVAC system. We'll start by tackling the challenge of per load operation, showing how simple reset strategies can slash energy consumption without sacrificing comfort. Our first objective is to explain how reset strategies at per load reduce coil and reheat energy and what their humidity implications are. Next, we'll analyze Economizers control using drivable versus enthalpy criteria and identify the free cooling regions. Then you'll learn to quantify ventilation load reduction using HRV, ERV effectiveness. You will also explain how to apply balances to DOAS, mixing to meet the latent and sensible targets. Finally, you will be able to select an airside strategy, whether it's CAV, VAV, or DOAS, and that aligns with the building's specific loads and indoor air quality needs. It's about choosing the right tool for the job. Before we dive into the details, let's start with a question to get you thinking about how HVAC systems can be smarter. You know that a building's cooling system works with removing energy from the air. We often think of this as simply lowering the temperature, but air also holds energy in the form of moisture. Imagine it's a dry day. The outdoor temperature might be a little warm, but because there's so little moisture in the air, its total energy content is actually quite low. So the question is, even if the air is a bit warm, can we still use it to help cool the building? Remember that what you remove in the cooling coil is energy. Think about how the system could use the low energy air from outside to reduce the job of the cooling coil, saving a lot of energy in the process. We will explore this and other optimization practices later in the video. This slide is all about making the system more flexible. The core idea is to reset the set points upward at high loads. Imagine a hot day. Your system runs at full power. But on a cooler, less demanding day, we can tell the system to slightly raise the temperature of the chilled water or the supply air. This simple change reduces the work of the cooling coil has to do. So the simple change reduces the work the cooling coil has to do, and critically it reduces the need for reheat. This is a direct attack on a major source of energy waste. So yeah, if you have a higher temperature air at the supply, then you are going to need less reheat. But there's a crucial caveat. You must guard latent control. We can't let the humidity run wild just to save some energy. Remember that the coil temperature is put at some level to reduce the humidity of the mixed air. So you cannot put it so high that then this effect of controlling the humidity is somehow is hindered. The coil exit must stay cold and near saturation to effectively pull moisture out of the air and keep the sun's humidity in check. If you get too aggressive with the reset, you'll save energy on cooling, but you might end up with a sticky, uncomfortable space, or in the worst of cases scenario, even mold, negating any benefit that you can have by having higher temperatures. And finally, you have to coordinate these strategies with your system minimum flow limits. At very light loads, a VAV system might hit its minimum airflow and start to overcool this space. This is when a modest amount of reheat can be introduced to maintain comfort, always ensuring proper air mixing and meeting indoor air quality standards. Building on our discussion on per load tactics, let's explore a powerful strategy to harness nature's own cooling: economizers. An economizer is a control that uses outdoor air to reduce or eliminate the need for mechanical cooling. An economizer's core job is to increase the outdoor air fraction to reduce mechanical cooling. A dry bulb economizer operates based on a simple rule. It ramps up the outdoor air when the ambient temperature drops below a specific set point. If the outdoor air temperature is low enough, specifically below the supply air temperature, the system can achieve entirely free cooling. So this means that if you need at your zone the air that you need in the supply is at the same temperature below or lower temperature than the outdoor air, then you can use the outdoor air for the supply air, and then you achieve free cooling. However, in very cold conditions, bringing in too much cold air might lead to overcooling, which then requires heating to maintain the zone temperature. So don't abuse of this. The more sophisticated approach is an enthalpy economizer, which bases its decisions on the air's total energy, or enthalpy. If the enthalpy of the outdoor air is lower than the enthalpy of the return air, the controller maximizes the outdoor air intake. This is a major advantage in dry climates, as it can still save energy even when the outdoor air temperature is higher than the sun temperature, because the coil load depends on total enthalpy, not just temperature. So this is related to the question at the beginning of the video. So yeah, remember that you remove latent and sensible and latent loads. So even if you have an air that is slightly over the sun temperature, because it's dry, you can have lower latent loads to remove. From a practical standpoint, this advanced control requires more complex sensors, such as those for wet bulb temperature or humidity, because you need two properties to define the air state. In addition to dry bulb temperature, while this improvement logic can lead to greater energy savings, which is why many systems still rely on simple dry bulb control despite its potential energy penalties. So yeah, because of the complexity of controlling from enthalpy, a lot of systems just rely on the dry bulb economizer. Regardless of the type, it's critical to always enforce a minimum outdoor air intake and include protection against freezing or overcooling in cold weather. So yeah, if you're in a cold weather and you bring too much outdoor air, then you're gonna overcool your zone. So continue with this discussion of economizer. Let's look at another powerful strategy for reducing the load on the system. There is energy recovery. This practice reclaims energy that would otherwise be lost to the outdoors. Energy recovery systems work by exchanging energy between the exhaust air leaving the building and the fresh outdoor air coming in. There are two main types: HRVs, heat recovery ventilators, which only transfer sensible energy, and ERVs, energy recovery ventilators, which transfer total energy, including both sensible and latent, so they also transfer moisture. We measure their performance using a term called effectiveness, which is the ratio of the actual energy transfer to the maximum possible transfer. So what we are doing with this recovery is we recover the energy that is going through with the exhaust air to get it back with the ventilation air. So the most significant benefit of this reduction in the ventilation load on the cooling on the cooling coil. The most significant benefit of this recovery is the reduction in the ventilation load on the cooling coil. With an ERV, the energy recovery ventilator, those that recover both sensible and latent load, so also moisture, both the enthalpy and humidity ratio of the incoming outdoor air are reduced. This directly cuts the cooling load and can sometimes allow for a smaller coil and system, while there is a slight penalty from the fan power required to push air through the device. The energy savings from reduced cooling are typically much greater. So yeah, in the you can have more you can need more fan power in these ERVs, but at the end, because you are recovering energy, the total energy you recover, it is worth it to do it, no? To quantify these savings, you can use the effectiveness expression, which for a total energy device is the expression that is there is a. For an HRV, you will use a similar expression based on temperature. So instead of having the enthalpies, you have the temperature. This is a relationship between the maximum that you can energy that you can recover and the actual energy that you recover. By combining this with the ventilation load term from our energy balance, you can accurately estimate the reductions in the coil load and the overall system capacity. So continuing with this, let's explore now a more advanced system architecture that fundamentally changes how we handle ventilation and cooling, the dedicated outdoor air system, or DOAS. This strategy is all about splitting the job to improve efficiency. DOAS is a clever system that decouples the ventilation stream from the recirculation stream. The dedicated outdoor air coil handles the ventilation air, cooling it to a low temperature to remove moisture and satisfy the sun's latent requirements. Meanwhile, a separate return air coil provides mostly sensible cooling to the recirculated air. The two three-tier streams are then mixed together in a plenum from the supply air. So you have separated. You have with the DOAS you have separated the ventilation stream and the recirculation stream. No? So now you have two different pipes that need to mix together, and this mix in a plenum, and this is the final supply air. Because the return coil doesn't need to be cold enough to dehumidify the air, because you have been because you are only using the dehumidifying the outdoor air, it can operate at higher temperature, which significantly improves the refrigeration efficiency, or COP, coefficient performance of the chiller. This approach also, because if you have higher temperatures in the coil, in the cooling coil, then the COP of the chiller is going to improve now, because you are going to have less difference between the evaporator and condensator. This approach also allows for a reduction circulation airflow, which leads to smaller ducts and big reduction in a fan power. To analyze the DOAS, you apply our familiar balances, but you do it for each path separately. You first apply mass, moisture, and energy balance to the outdoor air and return air streams. Then you mix them to ensure you meet both the sensible and latent loads of the sun. The key is to ensure that the humidity ratio of the air leaving the outer air coil is low enough that after mixing, the supply air meets the sun's latent requirement. So yeah, you have to be careful in the mixing. Now that we covered a variety of optimization strategies, it's time to put it all together and apply what we learned to real-world scenarios. This selection checklist and pitfalls slide will help you to make informed decisions and avoid common mistakes when implementing these systems. For an economizer, the first step is to select the right control logic, either dry bulb or enthalpy, based on your climate. You must always ensure that the minimum outdoor air requirement is met. Additionally, you need to include safeguards against freezing and overcooling and verify the performance of your sensors to prevent the system from operating counterproductively. When considering an ERV or HRV, it is crucial to confirm its effectiveness and account for the pressure drop and impact on fan power. So yeah, you're gonna recover energy, but because of all the piping, you need to see that the energy that you recover at the end is going to be higher than the fan power that you are going to need. You also need to consider the risk of condensation and the climate limits for the device. For instance, in the colder climates, condensate can freeze the HRVs, whereas ERVs are generally more effective at handling moisture. Yeah, if you're going to have outdoor, you're going to have warm air that is going to be cool. It's going to be cooling at these HRVs. Then you are going to have some condensation, and it could be even worse in colder climates when you can have a freezing. For a DOAS system, the key is to ensure that the outdoor air coil is capable of bringing the humidity ratio low enough to meet the sun's latent needs after mixing. You must also verify that reduced circulation airflow still provides adequate air distribution. A major benefit of this approach is its independence from indoor air quality, which helps avoid ventilation issues at low loads. Now, let's wrap up by summarizing the key takeaways from our discussion on advanced HVAC strategies. First, remember the power of the Economizer. This device can deliver substantial coil energy savings. In climates with a dry season, an enthalpy-based control is especially effective because it can still save energy even when the outdoor air temperature is a little warm, as long as its total energy content is low. So remember, we consider both sensible and latent load. Next, consider energy recovery. Devices like ERVs and HRVs effectively shift the ventilation load. ERVs are particularly powerful because they reduce both the temperature and humidity of the incoming air, often shrinking the required coil duty and design capacity enough to outweigh the slight fan pressure penalty. And finally, we have the DOAS, a game-changing strategy that fundamentally changes how a system operates. By decoupling and lighting from sensible tasks, a DOAS allows for higher return coil temperatures, which improve efficiency. It also enables a smaller circulation airflow and provides greater reliability for meeting indoor air quality standards, especially at low loads. So, before we conclude, let's look at some key concepts that build on what we learned, offering ways to continue learning about HVAC optimization. I want to invite you to check these advanced strategies such as Economizer tuning, ERV, HRV selection, and DOAS design variants. These are essential for achieving even greater efficiency and performance in real-world applications. To deepen your understanding, you could study Economizer tuning using psychrometric charts. These charts can map out different agricultural regions and help you consider using wet ball temperature as a proxy for enthalpy to improve performance when your sensor suite is limited. You might also want to compare ERV, HRV technologies, such as rotary wheels versus plates, and examine how their effectiveness translates into a specific ventilation load and design capacity saving across various climates. Finally, it's moving to explore DOAS variants. This includes, it's motivating to explore DOAS variants. This includes figuring out how to set outdoor air coil targets, choose the best mixing strategies, and manage the trade-off of reduced circulation airflow to ensure proper distribution. These design choices will sharpen your ability to deploy truly energy-efficient airside systems. Well, I want to thank you for watching this video, and let's continue learning. Bye.